The conventional split Hopkinson's pressure bar technique is a classic technique for high strain rate and large strain characterization of materials. This video will describe the procedure in which the split Hopkinson pressure bar technique is used to analyze the dynamic response of auxetic foams.
Auxetic materials are those characterized by a negative Poisson's ratio. When compressed, they undergo a contraction perpendicular to the applied force, as opposed to regular materials, which tend to expand transversely when compressed. The nature of this behavior can be understood on basis of particular cell structure.
Manufacturing auxetic foams.
Foam cylinders are cut out. They are then placed in a cylindrical holder which will aid in their transportation and compression process. The sample is then heated to a temperature which will allow it to become pliable. When heated to the specified temperature, the sample is then taken out of the oven and is ready to be compressed. It is placed in a vise and is manually compressed to a specified thickness. During this process, the foam's microstructure is modified and attains an auxetic character. It is allowed to cool in the deformed state.
After compression, the foam is taken out of the holder and its final thickness is recorded. The foams are submitted to impact tests using a split Hopkinson pressure bar, which is the standard method of analyzing the dynamic response of materials. The Hopkinson pressure bar was first suggested by Bertram Hopkinson in 1914 as a way to measure the stress pulse propagation in a metal bar. Later in 1949, H. Kolsky refined Hopkinson's technique by using two Hopkinson bars in series to measure stress and strain, incorporating advancements in the cathode ray oscilloscopes to record the pressure wave propagation.
Bars of different materials ranging from polymer plastic to steel and aluminum are used depending on the type of material to be tested. Testing procedure. The specimen is placed between the ends of two coaxial bars called the incident and transmitted bar.
The impact force imposed on the specimen is determined as a function of the pressure at which the striker bar is shot.
A striker bar is accelerated in a gas gun, which hits the incident bar, creating an incident wave. When the incident wave reaches the specimen, it splits into two smaller waves, a transmitted wave and a reflected wave.
The transmitted wave passes through the specimen, causing plastic deformation, and then is propagated into the transmission bar as a compressive pulse. The reflected wave propagates back down the incident bar as a tension pulse.
The magnitude of the strain experienced by the bars during this process is measured by strain gauges, which are connected to an oscilloscope. Run times for each test are in the ranges of 800 microseconds.
Time shifting of the collected data is used to determine the energy propagation throughout the bars.
A one-dimensional wave propagation analysis is used to determine the average stress, average strain, and average strain rate experienced by the foam.
Today we learned about the manufacturing of auxetic foams and the method behind the dynamic testing of materials using split Hopkinson pressure bar.
Applications of the study of energy-absorbent foams exist in areas where high impact response is required, such as ones found in the body armor and packaging industries.